So, hi everyone. Uh, in the past few lectures, we have been discussing about the non-idealities of Opamps. In this lecture, I'll try to wind up the few more non-idealities left to discuss. So, the goal is that by the end of this lecture, you should be able to read a datasheet, Opamps datasheet, and understand most of what is written in it. And we look at 2 to 3 products, 2 to 3 Opamp product datasheets, and try to understand or how are you going to pick an Opamp by reading its data sheet, okay, for your application. Now, coming back to the lecture, we have so far discussed three, in fact, we have discussed, I think, 6 Opamp non-idealities. I've shown 3 here, mainly the offset, input offset voltage, how to mathematically model it, and the problem of noise, and how to mathematically model it. We said input refer it and model it as a voltage source. Similarly, offset can also be input referred and modeled as a voltage source. And then we discussed other important parameter, which was called the input bias current. And we also define another parameter called input offset current. If a circuit is purely differential, perfectly matched, then ideally input offset current should be 0. Okay, and but if the circuit is asymmetric, which will normally be the case due to manufacturing errors, then you will have finite offset currents. So since we had some questions, okay, we saw the impact of offset currents on the performance of an op-amp circuit, and we saw some similarities between the input bias current and the offset voltage. So now I will take an example circuit to show you guys that they both can impact very differently. Okay, it looks like both of them have some kind of similarities, but I wanted to take an example to distinguish between the two. Okay, so first, so that's what I'll discuss, and then go back to other Opamp non-idealities. So consider this inverting amplifier with a gain of just -1. It's like a buffer, okay? And it's the circuit designer or the engineer had connected 2 feedback resistors whose feedback resistance of value 100 megaohms and the input resistance of value 100 megaohms. The gain is just -1. It's given that the offset voltage of this op-amp is 2 millivolts. Okay, and it's given that the bias current at the positive terminal, input bias current to the positive terminal is 150 nanoamperes. The bias current in the negative terminal is 200 nanoamperes. Now you have to tell me, by just quickly analyzing this circuit, which one can cause a problem. You can apply the principle of superposition to arrive at your answers. Just quickly try analyzing this problem. So we'll assume that you can apply superposition. Let's assume there is no input signal present. So assume only offset is present. If there is a 2 millivolt offset, I mean, by what factor will it be amplified at the output? Assume a 2 millivolt offset. By what amount will it appear at the output? I am saying the offset is 2 millivolts. Ignore all the other parameters. What will be the output voltage due to offset? It's a non-inverting amplifier, right? So the gain has to be 2. Exactly. So it's plus 2 millivolts, because I'm assuming VOS is positive. If I assume VOS to be positive, so it will be 2 millivolts into 1 plus R2 by R1. Right? It's a non-inverting configuration. Remember, if you recall from our previous lecture, you can model the offset voltage as a series voltage source to ground. So you're applying offset here, 1 plus R2 by R1. So it's a negative feedback. So the gain will be 2 millivolts into 2, which is 4 millivolts. So you will get output voltage due to offset is 4 millivolts. Okay, so that's what your offset voltage is doing to the circuit. Now look at the second non-ideality, which is your bias currents. Now can you tell me what will be the impact due to bias currents. The I plus really doesn't matter. It's anyways flowing into the ground. The inverting terminal bias current, IB minus, matters to us. And that entire current IB minus. So if you recall from basic op-amp circuit analysis, we are going to assume a current IB minus is going to flow into the op-amp. There is a resistance of value 100 megaohms here. Will this IB flow through this resistor, the other input resistor? What is the current flowing through this input resistor? 100 megohm resistor. The positive terminal is grounded. Zero, right? There is no current flowing through this. This guy, the current is zero. So which means all the IB has to flow through this. The op-amp's output will supply that. So if your IB is going to flow through this, you will have a current of 200 nanoamperes, which can be written as 0.2 microamperes. Multiply it with 100 megaohms. What do you get? You get 20 volts. And this op-amp, the maximum supply voltage is plus 15 and minus 15. And because of this bias current, the voltage that the op-amp has to go through is plus 20. Therefore, the output will saturate at plus 15 volts. So now you see the problem. In this circuit, offset is not a big problem. You designed an inverting amplifier, you put huge resistors in the feedback and the input path. Offset is not creating you much of a problem. Offset is just adding some DC shift at the output, and the DC shift value is just 4 millivolts. Not much. Okay? But the bias current, the input bias current, is creating a voltage of 20 volts. It's literally saturating the amplifier itself. So that's the problem. The output voltage is going to 15 volts. So in this circuit, if you see, the problem is because of the bias current and not the offset. The offset voltage, input offset voltage, is not a big deal here. Yes. So now the question one of you are asking is, yes, can we not just reduce the resistors? Why we are making this? That's exactly the point. The point I'm trying to show here is that the impact of the bias current will be dependent on not the ratio of the resistors, but on the absolute value of the resistors. Okay. We will see in the next example. I'll take a next example. In the next example, I'm going to build a cascaded amplifier. But if you look at the feedback on the input resistors, I'm having 10 kilo ohms and 100 ohms. 10 kilo ohms and 100 ohms. So can you tell me what is the combined gain of this amplifier? What is the gain from Vi to V0? What is the combined gain of this amplifier? 100 kilo ohm by 100. So the first stage is designed to give you 10 power 4. Okay, the first stage is supposed to, I think, yeah. First stage is supposed to give you a gain of, so this is 0.100, I'm sorry. First stage is supposed to give you a gain of 100. Second stage is supposed to give you a gain of 100. So the overall gain is 10 power 4. Now do the same analysis and tell me what will be the impact due to offset voltage first. Let's analyze the impact due to offset voltage first. Then we will analyze the impact due to the saturation current, the input bias currents. So can you tell me what will be the impact due to the offset voltages? First, analyze the impact due to first guy. Offset due to the first guy. What will be that? If you assume offset of 2 millivolts at the first guy's input, what will be the factor here? By how much will it get amplified? 1 plus R2 by R1. So that will be 1 plus 10K by 100, which is 100. So 101 times. So 101 into 2 millivolts. That will be the factor that will appear here. So that's roughly what? 200 millivolts. Okay. At the first stage, the offset is getting multiplied by a factor of 1 plus R2 by R1 and appearing as 200 millivolts. Second stage, again, it's getting multiplied by a factor of 100. So now what will be the output due to offset? 200 millivolts multiplied by minus of R2 by R1. Minus of 10K by 100 is 10 square, 100. So this is 200 millivolts. So you will get 2 into 10 power 4 or millivolts or 20 volts. Now, if you see, right, in this circuit, the offset of the first op-amp is literally saturating the output of the final stage. That is completely saturating the amplifier itself. Okay. So offsets usually are a very serious problem if you have very high gain. Okay. They are dependent on the gain. They are dependent on the ratio of the resistor values. Usually offsets become a serious issue if you are building very high gain circuits. Now let's analyze the impact of bias currents. In fact, I didn't even let me finish. Yeah. So one of you asked a question. I'll answer the question and come back to this one. In the previous question, the current cannot be supplied by the op-amp, right? The current that we are talking about is 200 nanoamperes. The op-amp has to supply a current of V100 by 100 megaohm or Vi by 100 megaohm, which will be a very small number, right? If your input voltage is within few volts, megaohm means if you will be consuming current, what, 1 by 100 megaohm. Volts by megaohms will be in the order of microamperes or nanoamperes. So op-amp will supply that current. But if it is saturating, the output will stay at 15 volts. It won't go greater than 15. The op-amp will start saturating at 15. And okay. I think your question is very valid. So what you're asking is, I need to supply a current of 200 nanoamperes. If I supply that current, ideally, if I supply that current, what should happen? This node voltage is at 0. So the voltage drop across this resistor will be much, much higher. Okay, it has to be 20 volts. What will happen? What will happen is that the op-amp will no longer be in negative feedback mode. Okay, the op-amp will go out of saturation. Yeah, that's a very good question. I'll probably take a minute to answer that and then come back to the next problem. So let me answer that this way. So the question that was asked is that I said that the op-amp's output will saturate to plus 15 volts. Okay. But if the op-amp is supplying 200 nanoamperes, if the op-amp is supplying that current, shouldn't the output go to 20 volts? It will go to 20 volts provided this node is at 0 volts, provided the input stays at 0 volts. Okay. But what will happen is that, yeah, what would end up happening is something like this. So the op-amp will no longer be in negative feedback. So you will have two resistors whose value is 100 megaohms and 100 megaohms. And we have connected the negative terminal to this node. Okay. So what should happen here is that if it cannot go greater than 15. So this node voltage will come to 15 by 2, close to 15 by 2. It will come to close to 7.5. And then if it is within the common mode range, this has to supply. Op-amp has to draw 200 nanoamps. So the only other possibility is if this guy is providing current in this direction. Okay, if op-amp is drawing 200 nano here, this guy will provide some current, and therefore this node voltage will come to no, ISAT is a very large value usually. So the question again you're asking is that I think your question may not be what I am looking at right now. What I'll do is towards the end of the lecture, let me finish this lecture. I'll come back to answer your point. But what you're asking is there any limit on the maximum current that the output can supply? Yes, there is. But in this case, it's not that big of a deal. This current is only 200 nanoamperes. That's not a big deal. It can comfortably supply that current, but it will be limited. It's not the example I took. It's not really, so maybe the node becomes minus 5 volts to make a difference. You're right. It has to do that, but it depends, right? If I'm connecting this node to you're right. So one of you said that node has to go to, yes, exactly. That is the only possibility where current can come from input into the op-amp. So that's what will happen. So you will see, you have a condition like this. You have a condition plus 15 volts, 100 mega ohms, a current source which is flowing in this direction whose value is 200 nanoamperes. And then you have a resistance whose value is, one side is grounded. I'm assuming input is 0. This is 100 mega ohms. Okay. If you have a current of 200 nanoamperes flowing this way, and the op-amp is let's say supplying this 200 nanoamperes. If the op-amp is supplying 200 nanoamperes, this node, I mean, it may not come to, see, you'll have to apply KCL and figure it out. Maybe the op-amp is supplying a lower current. It need not supply higher current. All I'm saying is that this node voltage will come to a value such that these two currents, you can quickly analyze that, what it will come to. Let's assume this is V minus. So you'll have a condition where 15 minus V minus by 100 mega ohm will be equal to, see, this is summing currents, right? I have to sum the current. 0 minus V minus by 100 mega ohms should be equal to 200 nanoamperes. So from that, you can easily calculate what VI is going to be. So you will get what? 15 minus 2 V minus equals 20, so 2.5 volts. So this will come to minus 2.5 volts. And the thing is that when this node voltage comes to minus 2.5, the circuit will go out of saturation. Your op-amp is no longer in negative feedback mode. Okay, so because your V plus is no longer equal to V minus. Okay, the op-amp is still, the op-amp is supplying a current of 200 nano. It's not, op-amp is no longer supplying 200 nano, it's supplying slightly lesser current, such that the input bias current happens to be 200 nano. That's like a current source, because that's how we model the input bias current. That will be a current source. Okay, that's a good point, guys. I'm happy that you're thinking in the right direction. Okay, so that's a good catch, because I didn't directly, I just wanted to demonstrate a point, but I didn't analyze, I didn't tell you what happens to these nodes. This node will actually come to minus 2.5 volts once it saturates. So if you actually, you probably might see this in a practical lab also. You can just take a MUI741 op-amp. Its current may be in this range, the input bias current. And if you put these large resistors, you might end up seeing this 15 millivolts, and this node might come to minus 2.5 volts. Okay, so it might happen. And the op-amp will no longer be in saturation. So if you look at the op-amp's characteristics, right, it looks something like this. Okay, there is an offset here. The output will be at plus 15 volts, but your input will be at, your V minus is at minus 2.5. So I can say V plus minus V minus is plus 2.5 volts. So you will be at this operating point. Your op-amp's output would have already reached close to minus 15, but it will be supplying a current of, it won't supply 200 nano. Maybe I think it will supply how much? You can calculate. So 15 minus 2.5, which is 17.5. 17.5 divided by 100 mega ohms. That's the current it will supply. So it will supply 175 nanoamperes. And the remaining 25 nanoamperes will come from this resistance. So so there is another question. In that case, some current is coming from the ground, but that is actually VI that we have considered as ground. So basically the extra current is supplied by VI. Exactly. Right. So input source, I've assumed zero source resistance. Because I've assumed zero source resistance, you can assume most of the current is coming from the input itself. right? I say ground is also like you can treat ground like a 0-volt DC source. So that current, you can treat it that it's actually coming from a 0-volt DC source. And this current is not very high, right? What the input is providing a current of 25 nanoamperes. 25 nanoamperes is not a big deal. That can be easily supplied. Even if you have a source with a finite source resistance, okay, it definitely will not be in the order of 100 megohms. It will be lower, little resistance will be little lower. It can still supply that. 25 nanoamperes is not a big deal. It can easily be supplied. Okay, so that's it. Yeah. So that's it, guys. That's a very good point. And if you actually build this circuit in a breadboard, you will see this. You will see this node B minus coming to minus 2.5 volts. Okay. Yeah, that's right. So now let's come back to this circuit here. Okay. So I just said that if you have offset voltage, the moment you have offset voltage, that can saturate this output itself. Okay. Yeah. Right now, I'm not worried about what happens to V minus. Let's assume that this is going to be a 200 millivolts. So maybe this guy will go out of saturation, and you can figure out what will happen to V minus. This guy will go out of linear range. So negative feedback will no longer hold true, and you will have So V minus will be at some voltage. Okay, you can figure out what that it is going to be. Okay, but all I'm trying to say here is that I'm now coming back to this circuit. So let me just, because we are recording it, I'll just mention it again. So in this circuit, we have a cascade of two integrating inverting amplifiers, each one providing a gain of minus 100. So minus 100 into minus 100, the overall gain is 10 power 4. Okay. Now we are similarly analyzing the impact of offsets and the input bias currents. So if I assume an offset of 2 millivolts for the first stage, we said the first stage will amplify by a factor of 101. Let's assume that's close to 100. So that will give me an output voltage of 200 millivolts. Now the second stage will again amplify by a factor of minus 100. So that will give me an output voltage of minus 20 volts. So your output should go to minus 20. So it will saturate at minus 15 volts. So all I'm saying here is that the offset of the first op-amp itself is saturating the second op-amp. Okay, I don't even have to worry about the second op-amp's offset. Yes, let's assume the second op-amp's offset is 2 millivolts again. Multiplied by the gain of 100, it's going to cause plus 200 millivolts. Okay, but since it is already saturated to minus 15, I mean, this guy has the first stage offset is taking it to minus 20. So it will very comfortably be saturated at minus 15 volts. Okay. Now analyze the impact of the bias currents. If you start with the bias currents, the first stage bias current is really low. What is the value of the first stage bias current? 200 nanoamperes. So 200 nanoamperes flowing through 10 kilo ohms. So that is 0.2 into 10 power minus 6 is the current. Multiplied by 10 kilo ohms is 10 power 4. So that will be 0.2 millivolts. 10 power minus 2. So which is 2 millivolts. So the voltage change due to the bias current is just 2 millivolts. Multiply 2 millivolts by 100. What will you get? Minus 200 millivolts. Again, not much of a big of an impact when you compare it with the offset. It is actually causing a delta of 200 millivolts, but the first stage offset is so high that it has saturated second op-amp's output. So all I'm showing, I just showed you an example in the second case where input offset becomes the limiting problem. Okay, that limits your performance. That is saturating the second op-amp's output. Bias current is not doing much. Okay, so I just wanted to take two examples, and now you guys can now quickly see when can this happen. If your feedback resistance is really large, then bias currents can have much of an impact. Okay, if I put additional amplification after that, that can amplify it further. Okay, but it usually depends upon the op-amp where the feedback resistor is large. Okay, if the feedback resistance is large, then you have bias current itself can saturate that op-amp's output. Generally, when you have very high gain circuits, you have to then worry about offsets. Offset can become a serious problem. Okay, so I just took this example to show you guys the difference between how offset and bias currents can impact circuits very differently. Okay, that's it. So far, I'm listing what we have discussed in the previous 3 to 4 lectures on practical op-amp circuits. We spoke about DC gain. Okay, that is the DC gain of the amplifier. Usually it is in the range of 80 to 120 decibels, or maybe it can be, plus 10 minus 10 on either sides. Okay, high DC gain is always good. So when you're going to pick an op-amp, always pick an op-amp with really high DC gain. Okay, the second one is gain bandwidth product. Gain bandwidth product is a measure of the maximum frequency you can apply to this op-amp and expect faithful amplification. Okay, the circuit will behave exactly as you analyzed it using ideal op-amp models, but until this frequency of given by the gain bandwidth product or unity gain frequency. Generally, it will be in the order of a fraction of a megahertz to even gigahertz. High performance op-amps, which will be used for very high frequencies, may have gigahertz of gain bandwidth product or UGB. So your mu 741 that you use in the lab will have in the order of megahertz. Next thing we discussed is the input noise. Input noise is usually not a big issue when you're concerned about functionality. Okay, when you're considering just functionality, input noise won't matter much. But when you talk about performance, then it will matter a lot. Okay, if you're worried about amplifying with great fidelity, when I say use the word fidelity, I mean very clean amplification, then noise becomes a major concern. And noise, usually we mention it as a noise floor. The units will be in nanovolts per root hertz, and it can vary from the units of the noise can vary from few nanovolts per root hertz to microvolts per root hertz. So microvolts per root hertz means very bad noise, very bad op-amp. It is very noisy. The op-amp is very noisy. And if performance is a very important factor for you, you'll have to pick an op-amp with very low noise, okay, which will be in the order of few nanovolts, 0.1 nanovolt or 0.2 nanovolt per hertz. These are very low noise numbers. Next one is input offset voltage. This we said is it can occur because of how the op-amp is implemented, because of mismatches. All that will cause input offset voltages, and that can be from microvolts to millivolts. Your MUA 741, we will look at the data sheet towards the end of the lecture. It will be in the order of millivolts. Then we looked at input bias current and input offset current. Okay, this is to bias the input pairs, and again that current can vary from picoamperes to microamperes. And usually the bias current will be very high for BJT-based amplifiers, BJT-based MOS op-amp amplifiers. Okay, and generally sometimes you can get BJT amplifiers with very low input bias currents as well. Okay, there are some techniques using which we can reduce the input bias currents. So those op-amps will be priced higher. Your MUA 741, again we'll look at the data sheet later. It will be in the order of hundreds of nanoamperes. Offset current can also be in the similar hundreds of nanoamperes range, okay? Pico to microamperes. And usually it will be picoamperes for field effect transistors, DI-FET, MOSFET-based op-amps and all that. So generally, BJT-based amplifiers will have very high gain bandwidth. Okay, BJTs are generally known for it. It's actually a very good device for analog engineers. Okay, but usually what happens is digital is the world is majorly digital, right? Digital analog is a very small part of the world. If most of the electronic devices that we use, they have huge digital chips. Analog will be very small if you compare with the digital operations. So because digital, they go for CMOS technology. Analog engineers are now forced to use CMOS because it's cheaper, and then we can build circuits using that. But generally, BJTs offer better speed performance. Okay, but you will have a problem of input bias currents. So what they do is that you might have heard of this word called BiCMOS, where they use both bipolar transistors and MOSFETs. They use bipolar transistors to get the bandwidth, and they will use the MOSFETs to lower the bias currents, the input bias currents. So these are again a class of amplifiers, but these are not, you won't find them in such large numbers, but they will be for very specific applications. Let's say your high performance applications, you want very low bias currents. Okay. But you also want very high speed. Then you'll have to go for a BiCMOS solution. And there are dedicated teams, you'll have teams in TI or ADI building such kind of op-amps. Okay. That's it. So now we have discussed a range of parameters. Okay. We have few more parameters to discuss, and I'll discuss them in the next half of this lecture. So what happens is an engineer is trying to build a op-amp based circuit with a gain of -100. So he's building a very simple circuit to amplify a signal which is going from -100 millivolts to +100 millivolts. A sinusoid, he just wants to amplify it. Before maybe he's feeding it to an ADC or some load. Okay. It turns out the gain bandwidth product of the op-amp is 100 megahertz. Bias currents are very low. They are in the order of picoamperes, and offset voltages are also very low. It turns out the op-amp is of a very good quality, and turns out offset is also not a big deal. He's feeding a sinusoid of ±100 millivolts. The gain is 100, right? So multiply by 100, you should get ±10 volts at the output. He is expecting a pure sinusoidal output of value where it has to go from ±10. But instead, he observes a very weird waveform. The waveform looks like a triangular waveform at the zero crossings, and it looks like some kind of a sinusoid. The green waveform, ideally is expecting the yellow waveform. Okay. But what he's seeing is a very weird waveform. It's a very distorted waveform. Okay. So the input frequency that he's feeding is just 100 kilohertz. And he just reads the data sheet and he sees the gain bandwidth product is 10 megahertz. And his input frequency is 100 times lower than that, which means it is well within this safe limit, right? What does gain bandwidth tell you? It tells you what is the maximum frequency you can apply to this circuit and still expect it to operate, okay. So let me, for example, I think maybe in this circuit, let me assume the gain bandwidth product is 100 megahertz. I'll explain later why I took 100 megahertz. The feedback factor is 1/100 for this case. So I'll probably, in the next class, it will become much clearer, but let's assume it is 100 megahertz instead. Okay, instead of 1 meg, 10 meg, let's assume 100 megahertz. 100 megahertz, so still it is much lower. It's much higher than 100 kilohertz. Okay, I just took this 100 megahertz to avoid any practical problems. So that's why let's ignore about that. It doesn't really matter. All I'm trying to tell you guys is that you're applying a sinusoid of frequency 100 kilohertz, which is well within the safe limit, right? It's much lower than the gain bandwidth product. But he's seeing a very weird output. Okay, offset doesn't explain it. The bias currents are also not explaining it. Noise is also not much. I mean, ±10 volts is a huge signal. Noise won't really be that much of a problem. Okay. So then what he does is that he reduces the amplitude from 100 to 10 millivolts. 100 to 10 millivolts, and he observes a perfect sinusoidal output. Okay. So now, if you take the Fourier transform of this green colored waveform, right, this 10 volt waveform, you will find a lot of harmonics. I mean, because it's a triangular waveform, right? A sinusoid will have only one harmonic, which is 100 kilohertz. For an LTI system, an ideal linear amplifier, the output frequency should be exactly the same as input frequency. For a nonlinear amplifier, you will find a host of other frequencies, usually harmonic, a multiple of the input frequency. So you'll find 300 kilohertz, 500 kilohertz, and so on. Okay. So now he's worried, why is this distortion occurring? To explain this, none of the previous non-idealities can account for this. Bandwidth, gain, these are all linear parameters. They don't account for it. To explain this, they have to introduce another parameter called the slew rate. Okay. Slew rate is defined when the op-amp's output is not able to increase at a rate as predicted by linear analysis. So I'll just go through the mathematics. Let's say you apply an input signal, which is V peak time cos omega nt. I mean, it can be sine also. It's just cos omega nt. Omega n is the input frequency. So the output signal is supposed to be the gain of the op-amp. In this case, it is minus 100. Gain of the inverting amplifier, which is minus 100. Minus 100 times Bp into cos omega nt. What I'll do is I'll differentiate this. If I'm asking you what is the maximum rate of change of this sinusoid. So anytime you look at a sinusoid, the slope of a sinusoid keeps changing. If you see, a sinusoid doesn't have a fixed slope at all time instances. It has the maximum slope at the origin, at the zero crossings, and minimum slope at the peaks. If you find the slope at the peak, right, it's going to be zero. Okay, there is one point, it's not changing much. Even if you move at the peak of a sinusoid, you are moving by delta t, but the amplitude change is zero. So which means the slope is zero. So sinusoids have a maximum slope at the origin. So you can verify that quickly, differentiate this waveform. You will get ABP. If you differentiate cos, you should get sine with a negative sign. So let's not worry about the sign. Let me write mod of this. I'm interested in the magnitude of the slope. You will get AVP omega n times this. So the maximum slope, because the maximum value of sine is plus minus 1, right? If a maximum value is plus 1, so the maximum value of the slope is simply AVP times omega n. Okay, so that will be A times the gain of the amplifier times the input voltage peak times 2 pi Fn. So in our example, Fn happens to be 100 kilohertz. If you substitute 100 kilohertz here and 2 pi, round it off to 6, no, 3.14 into 2, close to 6. Input amplitude is 100 millivolts, so 0.1 volts. Gain of the circuit is 100. So if I multiply that, I will get a term which is nothing but 6 into 10 power volt hertz. Or I can express this as 6 volts per microsecond, which means if you advance by 1 microsecond on the time units, the output can change, the sinusoid's output can change by a maximum of 6 volts. If you move by 1 microsecond, the delta V, the delta Y, change in the y-axis or the output voltage will be 6 volts. This is the maximum slope of a sinusoid. It depends upon two things. The peak voltage or the gain of the amplifier, I can club these together and call it output voltage amplitude, right? So this is VOP, is the output voltage peak into omega n. It depends on two things. It depends on the input frequency and also on the output voltage. Okay, so generally for a practical op-amp, there is a maximum rate of change of the output. Okay, and that maximum rate of change is what we call slew rate, which means your op-amp's output cannot change at a rate greater than this. Okay, so that's what we call slew rate. And it turns out for this op-amp, the slew rate is 0.5 volts per microsecond. If you see here, right, this is 6 volt per microsecond. So, and the slew rate is maximum slope is 0.5. That is why the op-amp was not able to track it. Ideally, the op-amp should increase at the rate of 6 volt per microsecond, but the op-amp's maximum rate of increase is only 0.5, 1/10 of it. That is why it was failing to increase, and which is why you are seeing a weird ramp pattern. Okay, ramp means whenever your op-amp is increasing in a ramp fashion, we use a word, we say that the output is slewing, which means the op-amp is now reached its maximum rate. So why does it happen? I'll give a very small example. So I'm giving an example here. All I'm showing is the output. The maximum slope with which the output can raise is called slew rate. Since you guys have already done ADVD, maybe you have some idea. I'll just quickly refresh your memory. Let's take a very simple 5 transistor amplifier. Okay, so remember, keep this in mind here. So I did not observe this problem when my input signal level was very low. Okay, or let me take this to be 0.6 volt per microseconds. Okay, so that, you know, instead of 0.5, for analysis sake, let's assume this is 0.6 microvolt per second. So now if you see, right, if I apply a 10 millivolt sinusoid, the output is going to be plus minus 1 volt. Now the maximum slope of the output is approximately 0.6 volts per microsecond. This is within the slew rate of the op-amp. So your op-amp output is able to track. It's able to change at a very high speed here. Okay, usually the waveform will not match in this range. Once the sinusoid reaches its peak value, right, there the slope is lower. So it will be able to track at the peak, which is what I've shown here. If you look at the green curve, it's able to track the output, desired output waveform near the peaks. It's unable to track it at the zero crossings. That's where it is completely failing. Okay, but in this case, it's able to perfectly track. So you see, right, the problem is not frequency. Frequency was fine because it is well within the UGB. The problem is the input amplitude. Okay, so therefore, slew rate is a large signal phenomenon. When you apply larger voltage signals, that is when you will see this problem of slew rate. Okay, so slew rate becomes a problem when your signals are very large. So think like this: whenever your op-amp output is charging, right? Whenever your op-amp output is charging, it means, what does it mean? Op-amp is supplying an output current and it is charging this node. There is some, you can picture some node capacitance at the output terminal, and some current is flowing through the cap and charging this cap. That's what is happening at the op-amp's output. Okay, and when this current is being flowing, I mean, see, nominally when the input voltage V plus and V minus are equal, there was some nominal current flowing through the circuit. Okay, if I'm saying that the output voltage is increasing, which means some current is flowing from the op-amp. For that current, a current is an action. Okay, it is a reaction. That current is getting pumped out of the op-amp because a small delta V appears across the input. A small delta V appears and it will push a current. Okay, that's how the change happens. If you assume the op-amp to have finite gain and all that, then a small delta V appears and it pushes that current. Okay, if the delta V becomes larger, which will happen when you have large voltage swings, then op-amp has exhausted its maximum current it can supply, and it will say, I cannot charge this node any faster. So let's take a very simple example. Let's take an example of a 5 transistor differential pair, which you guys must have analyzed it. How do you measure slew rate? We take a differential amplifier. Let's say we bias them to some common mode voltage. So I'm going to keep this at some common mode, and I'll apply a large step input from V common mode. When I apply a sudden large step input, what will happen? All the current will switch to one side, right? It's a differential pair. You guys know that whenever you apply a large differential input to a differential pair, the current will completely switch to one side. This current will go to zero. So this op-amp will not carry any current. This is a current mirror. It's simply going to mirror this current. So this entire IS, the source current, the tail current, will flow into this capacitor. And IS by CL is the maximum slope with which the output can rise. Okay, so the output voltage is simply given by IS by CL times T. Right? You push a constant current into a capacitor, it will just integrate. So if it integrates, you will get a linear voltage like this. And the slope of this linear voltage is IS by CL. Even if I increase my step voltage any further, that slope will not change. Okay, so that's why it's the maximum rate of change of your output signal. That is, I've taken a very simple example to show you guys, since you have already done MUV and ADVD, you can understand that how this limitation comes, where this limitation comes from. Okay, because there is the maximum current that the output can supply is limited. Therefore, that limits your slew rate. So that is why this is another specification which needs to be mentioned alongside UGB. Gain bandwidth alone is not sufficient. You have to also mention slew rate of the op-amp. Okay, slew rate will tell you whether you can apply a certain maximum voltage or not. Okay, so that's why slew rate is a very important specification. It captures the maximum rate at which your output can change, and from that you can back calculate what is the maximum peak voltage you can apply to this circuit. Okay, and if your op-amp's output is constantly ramping like this, then we say that, okay, the op-amp's output is slewing. Okay, it means that it cannot increase at a rate much any faster than this. So that's Slew rate, a very useful parameter. It's a large signal. See, gain bandwidth product is a small signal parameter, right? We used a linear model for the op-amp, a linear model, LTI model for the op-amp using small signal models. And then that's how we got this. We derived this from a UG, from a Bode plot. Bode plot is a small signal response, right? It's a AC response of the amplifier. So it's a small signal model. So you get gain into bandwidth product. Okay. Slew rate, on the other hand, is a large signal parameter. Now, if you see it, I'm measuring slew rate from a transient simulation, from a time domain simulation, not an AC analysis. And I'm applying a sudden step, a large input difference, and then seeing how much current it is pumping, and then measuring the slope of your output signal. And it will vary from architecture to architecture. If you choose a different op-amp architecture, it will change. So that's slew rate, and we have to mention this as well. So bandwidth alone is not sufficient. So slew rate will explain this behavior. What will explain this? Nonlinear behavior at the, especially at the zero crossing, your output op-amp is not able to trace the ideal output, and that's because of slew rate. Okay. So there are only 3 more parameters which are very trivial, very easy to understand. I'll finish this in 5 minutes. Then we can go to start reading the data sheets. The other thing that we left out, and meaning we already know this, but we didn't discuss it, input resistance. I said, ideally, if you look at the input impedance of a op-amp, it has to be infinity. Okay. But we know if it's a BJT based amplifier, we are looking at the base of the BJT, and generally it will be, R pi, right? The BJT has a model, small signal model, so it will be finite. All I'm saying is it will be finite. Generally, for BJT based op amps, it will be in the order of mega ohms. For MOS based op amps, it will be in the order of giga ohms. Okay, because for a MOS based op amp, the input is is an oxide. Okay, so it's a insulator, so it will have much higher input impedances. So for a your 741 op amp that you guys use in the lab, it will be in the order of mega ohms. You can measure this. Okay, you can, in fact, you can use an ammeter to try and measure this, but you have to measure it. You have to power the op amp and measure it. Okay, so you have to be a little careful. It's not, you can't easily measure it using a voltmeter. Okay, you'll have to do some small tricks. You have to do some small tricks to measure this. Okay, it won't be easily. You can't do it using voltmeter. Is all I'm saying. Okay, so the next one is output swing. Output swing is the maximum peak-to-peak voltage that the output signal can take. We have already discussed this when we spoke about saturation voltages. So generally, it will be close to plus VCC and minus VCC. The peak voltage will be very close to that. Maybe few hundred tens of millivolts or 100 millivolts lower than the peak supply voltages. But generally, you can go as high as the supply voltage. Okay, so that will be it will be mentioned in your data sheet. Or if they say that you have to be 100 millivolts lower on either side, that is mainly for linearity reasons. You don't want to push the op-amp to the extremes where your output waveform starts distorting. You don't want that. So maybe you can keep some small margin. A few 100 millivolts should suffice. Okay, that's output swing. The other, which is important and slightly intuitive to understand, is the input voltage range. You will see this input voltage range also in the data sheet. For circuit designers, we call it input common mode range. We will call it ICMR. So to understand this input voltage range, so let's take a simple circuit. We have to understand it using a buffer or a voltage follower. Because if you see this circuit, right, if you take a inverting amplifier, V plus and V minus always stay at 0. They don't change at all. So usually we don't really care. In inverting configurations, usually these two terminals will be calm, they won't change much. But in non-inverting amplifiers, whether it's a non-inverting amplifier or a buffer or a voltage follower, if you see, right, V plus will be equal to V minus, and output voltage will also go through same swing. So if I apply a sinusoid of voltage V peak to minus V peak, output voltage will also go through the same swing. It will be V peak and minus V peak. output voltage is connected to the inverting terminal. So inverting terminal will also go through the same swing. So if you see, right, both V plus and V minus are both equal to Vi. So both the inputs are raising. When the input signal is going as a sinusoid going through a zero and peak values, both these inputs are raising together. So as far as circuit is concerned, it will look like a common mode input. Okay, it will look like a common mode, right? Both are changing together. And we know from circuit basics that if you take any MOS-based differential pair, there is a range of input common mode values for which the circuit will work, right? So if you keep lowering the DC value of both these inputs, can you guys quickly tell me what is the minimum DC value needed at these gates? Because you have done basic course on MUI, what will be the minimum value needed? Let's assume the current source needs a voltage of V tail to keep that in saturation. What is the minimum V common mode needed? Plus Vt or plus VGS. You will add some margin. Assume that this device is carrying some bias current. See, when you're applying common mode inputs, usually you will assume both of them are carrying some bias currents. So it will be 1 VGS plus 1 V tail. That will be the minimum voltage it can go to. Maximum it can go as high as supply voltage. Okay. So this range of voltages for which this circuit will operate properly is what we call ICMR. And that ICMR will be referred to as input voltage range here. Usually, the input voltage range will be 2 to 3 volts lower than the supply voltages. See, if supply voltage is plus 15 volts, if this is minus 15 volts, it will be 2 to 3 volts. It will be like plus minus 12 volts or plus minus 13 volts. So even if you are building a voltage follower circuit, you just look at the data sheet and see that the output swing is plus minus 15. And then if you apply a plus minus 15 input, right? If you apply a plus 15 and minus 15, you will not see a plus 15 and minus 15 at the output. That is because the input common modes don't change. The input common modes have a range limit. Input is telling you you cannot apply a common mode greater than plus 13. So you have to limit your inputs to the input voltage range. Usually this is a problem. The input voltage range is very important for you when you're designing voltage followers or if you're designing non-inverting amplifiers. Okay. Input voltage range is not a big deal when you're designing inverting amplifiers. So that's because usually you will keep the common mode voltage at this node. I've grounded it here. You will keep it well within the desired range. So we don't have to worry, is all I'm saying for this circuit. Whereas in this circuit, in voltage follower and non-inverting amplifier, this matters. The input voltage range, it's called as input voltage range. It's essentially ICMR. Okay. So the ICMR should be within your input signal that you apply should be within the ICMR, the range of the input common modes. I'm saying that value will be generally 2 to 3 volts lower than the supply volts. So if your supply voltage is between minus 15 and plus 15, your output voltage swing will be as high, but your input range, right? So this is your input voltage range will be slightly lower. It will be plus minus 2 volts on either sides. So you can only apply sinusoids in this range. Okay, especially it matters when your amplifier happens to be a voltage follower and you want a near rail-to-rail outputs. Okay. Yeah, so we have 5 minutes of time. I'll just discuss one. So now I've told you guys about input common mode range. There is one other final parameter, and I think I forgot to mention this. And then I'll quickly take you through the data sheets. And that is called output short circuit current. Okay. Output short circuit current is the maximum current that the Opamp can supply when you short circuit the output node. So let's say you're building an amplifier with an inverting amplifier like this I've shown in the circuit. But this amplifier is driving a load resistance. The load can be an ADC's input, or it can be an audio amplifier's input. Okay, audio amplifiers input, a loudspeaker can have very low resistance, which means you have to supply a lot of current. In such cases, if I make RL go to zero, theoretically the op amp has to supply infinite current. But what happens in practice is that as you supply more current, there will be I square R losses in the circuit. Losses means more heat. Your op amp can be damaged. More current means more losses, more heat. More losses means more heat, and heat will generally damage the chips. For safety reasons, they will normally limit your output current to a certain maximum value. Okay, so that's called output short circuit current. So output short circuit current is mainly for thermal protection, and the maximum current, that how do you measure that? You almost short circuit your load. Okay, if you see, if I ask you what is the total current the output has to supply, it has to supply the current to the load resistance. It also has to supply the input, whatever current the input demands for its normal operation. How do you measure output short circuit current? By shorting this load. You make this load go to zero and measure the current the op amp is supplying. That will be your output short circuit current. Okay, or make this resistance as low as possible. Keep decreasing it. At some point, your current will saturate. It won't increase any further. That will be your maximum output current or the short circuit current. So normally what you do is that, let's say you purchase an op amp and it turns out you need to serve a load resistance, and you look at the data sheet, and the data sheet tells you that the short circuit current is 10 milliamperes. But it turns out you want to drive a load whose you have to supply, say, 40 milliamperes. Either you purchase a higher op amp with a higher current, or you can take an op amp with a lower short circuit current and do some modifications. You can just insert a BJT in between. This is like an emitter follower. And BJT, this BJTs, if you look at it, you get different flavors of BJTs. This BJT has to be a high current BJT. High current BJTs are often called power BJTs. They will be able to carry larger currents. Okay, they will be bigger in size itself. You can look at the size physically, they will be bigger in size. Okay, put this in feedback, so that, why am I putting this feedback? So that this output node voltage V0 will be exactly equal to minus of R2 by R1 times Vi. I'm delivering the right power, but this BJT will supply that current. Now, just keep one point in mind. The BJT can only supply current because it's a NPN BJT. It can supply current only in one direction. Okay, we'll talk more about this in the next lecture, but I just wanted to introduce this concept of short circuit current, the maximum current you can deliver. So now we are done with most of the specifications for an op amp. So generally this is a very dry part, but I tried to take examples to make it exciting. But the more exciting part is how do you build interesting circuits using this. But even though it's a dry part, it's very useful because you will be able to build high performance circuits only if you understand all the specifications. Okay, see, what are specifications? Specifications are nothing but conditions. Under these conditions, your op amp will behave as you want. Your op amp will behave like an ideal op amp. If you go out of this range, if you want your output slope to be higher than the slew rate, then you can no longer expect it to behave like an ideal op amp. Okay, so what are specifications? Are nothing but they are like conditions under which your op amp will behave as desired. So that's it. Now we have all the answers. This is a typical data sheet of a 741 IC. I've just taken it. If you just stare at it, you guys can now understand most of the things. You know what input offset voltage change stands for. And if you look at this number, right, it's typical 1 millivolts and maximum is given as 5-6 millivolts. Again, we saw in the previous lecture, how is this measured? You measure it for multiple parts and then plot a Gaussian PDF kind of a plot. You'll have a mean, and usually within 1 sigma on either directions, that will be the value that is reported as typical here. Maximum will be 6 sigma. You take the 6 sigma values. That's why if you see, right, 1 and 6, close to. I'm just giving you guys some rough number. It will be sigma and 6 sigma. That's what they'll report here. Then input voltage adjustment range. So this is nothing but a programmability. We'll talk about this later, or it's not a big deal. It's just like your offset nulling advantage. You can vary the offset. Okay. The next thing is input offset current. We know how to measure that. Input bias current. We saw by looking at these numbers, you can see input bias current. If you see, right, it's 80 nanoamperes. This is because, immediately you can say it's a BJT based op-amp, which is a LM741. It's a BJT based op-amp. For MOS based op-amp, you will see that these numbers will be in the picoamperes range. Okay. And they've also given you max. Usually when they report a product, they'll report a min and max values. They'll also be temperature dependent. All BJT currents have a very strong temperature dependence. So they will be temperature dependent. They've given you range. So this will be useful for you in analyzing your circuit. You may have designed it for typical and it worked perfectly. But at some temperature, the currents can increase by 2-3 times and it might fail. So that information will be given in the data sheet itself. Input resistance, we just discussed it and I showed this number is close to 2 megaohms. Okay, this is for BJT. For MOSFETs, it will be in gigaohms. For MOSFET based op-amps, it will be in gigaohms. Input voltage range, this is like ICMR. And if you see typical number, it's plus minus 13 millivolts. Okay, this is the range of input voltages for which your op-amp will behave like an op-amp. Okay, like a ideal op-amp. Output voltage swing, if you see here, output voltage swing, it's not plus minus 15. They have reduced 1 volt. Okay, so the output voltage swing, they have reduced 1 volt. And here they have measured it for different loading conditions, 10 kilo ohm and 2 kilo ohm, because it also depends upon how much current you want to supply to the output node. So I'll go a little bit more detailed, probably a little later. But all I'm saying is, look at this. This is higher than the input voltage range. You will have to give few hundreds of millivolts on either sides for biasing the transistors. Okay, for output node, but it will be slightly higher than the input voltage range. Output short circuit current for a MUA 741 is 25 ampere. And you understand what is the significance of this. Okay, so this tells you the maximum current that you can provide to your load. You can never exceed this number. Your op-amp will not exceed. If you want to exceed that number, you will have to do some modifications to your op-amp circuit. Either purchase an op-amp with a higher output current or add a BJT. An emitter follower will solve your problem. I'll come to common mode and supply rejection ratios when we talk about instrumentation amplifiers. It makes sense when we discuss that. Right now, we can ignore this. Transient response is not a big deal. Again, I'll come to that. These two things, what slew rate is. Slew rate is a very important parameter, especially if you are going to apply large signal inputs. Okay. This data doesn't contain UGB gain bandwidth. It is present in another data sheet. So we'll look at it there. Okay. So maybe let me see if I can show you guys some data sheets for op-amps here. So look at this. This is a TI data sheet for a very good precision amplifier. Precision amplifier means amplifiers which are designed for better performance. If you see, right, they are highlighting the noise number here. So this noise number, they are highlighting 1.1 nanovolt per root hertz. That means it's a very low noise op-amp. Okay, it's a low noise op-amp. And so if you want a low noise, you will have to pick an op-amp with a lower noise. So look at this. This is the features that it's a marketing tool. They are just listing out all the things that you need to know. Based on what you have read so far, at least you should be able to read 50% of this. What you have understood so far, at least 50% of this should be clear to you. Okay. Then you can pick your right op-amp for your applications. So I think, we have discussed many things. So I'll stop at this point and then I'll open for a quick discussion and then we can close.